Welcome to the interim presentation for Team 35. Our group members are Mahmoud H., AJ Kraus, Brady Nordbeck, Henry Persons, Lark Sawyer, and Audrey Safer. For our project, we analyzed a food dicer. This product quickly and consistently dices items when preparing food. The mechanism completes the dicing process in two cutting steps. The dicing process is performed when the user utilizes the top presser to perform a vertical slice and then uses the handle to complete the dicing process. From our market research, we determined the U.S. demand to be about 11.8 million. We identified the primary customer to be commercial kitchens and restaurants due to the size and cost of this device, with the secondary market being home cooks. Our product analysis begins with an exploded view of the mechanism. The frame serves as the base for the entire mechanism, housing the grate. Parts 4 through 10 comprise the linkage subsystem using 3 rods, 2 of which are the same length, and the last being longer, which extends to the frame and grate, connecting the entire assembly.
For the first assembly sequence of the food dicer, the frame is set down and each part is added individually one after the other. As seen in the previous slide, many parts have to be fed through the frame, which makes it difficult to form sub-assemblies prior to adding parts. With the second assembly sequence, smaller sub-assemblies are built before adding these to the frame, such as the handle sub-assembly, as well as joining the small links and the end caps together prior to adding these to the frame. When evaluating these assembly sequences, the reason for sequence 2 being obviously better is due to the fact that smaller sub-assemblies can be formed before adding these parts to the frame, which means that there are less parts that the person has to hold while adding parts directly to the frame. One of the many inefficiencies with both sub-assemblies that we plan to improve on is the fact that many parts have to be fed through the frame, as well as the aforementioned reason of not many sub-assemblies being able to be formed before adding them to the frame. And these are things that we plan to improve on.
Before redesigning the food dicer, we first need to gain a better understanding of the product's functionality and how that relates to the product's current design. We start by creating a fast diagram which identifies 2 primary basic functions. Importantly, the cut food function is broken down to emphasize the 2-step cutting process, which uses the top presser for the sliced food step and the back presser for the diced food step. In addition to the basic functions, a number of supporting functions that improve the quality and usability of the product are identified in the lower 4 branches of the diagram. The terminal functions of the FAST diagram, highlighted here in green, are used to create function component mapping matrix to identify the couplings between the product's functions and parts. The scattering pattern of X's rather than the diagonal pattern indicates a high level of function sharing. Furthermore, we can see that parts 4 through 10, which comprise the linkage subsystem, often operate together. To quantify the importance of a single component in realizing the product's function, we denote a component as of high importance if it contributed to more than a third of all the product functions, as color-coded here.
Our goal with our dicer was to cut down our assembly costs and enhance customizability. An essential step was to create a bill of materials, or BOM. Our tooling cost per product is estimated to contribute less than 1% of our total cost due to large estimated product demand, and is thus negligible. Also, we estimate a 50% scrap of material for any injection molding and sheet metal, which is otherwise estimated based on per kilogram material cost. Our BOM assumes all parts are relatively simple geometries, with no need for any high tolerance or surface finish, which reduces process time and allows for negligible process cost. Our estimated total cost of $54.25 is validated by comparison with similar products which have retail costs ranging between $15 to $1,000. This BOM is color-coded, with high-cost parts in green and low-cost parts in yellow. High-cost parts are estimated to be more than its share of the total cost, minus the grate cost as an outlier. Importantly, the grate is the heaviest and the most expensive part due to its volume of stainless steel. The quad chart organizes the parts by 2 main criteria: production costs and functional importance, both with high and low subcategories. We will focus our redesign efforts on the parts that are high cost and high importance.
Now we are going to talk about the food dicer's product family, designed to cater to the needs of different customer groups. In our case, the 2 major groups are professional chefs and home chefs, who will both be using the device for the same main purpose, reducing the size of food. The main difference we have identified between the needs of these 2 audiences is the need for uniform-sized pieces of food. In a restaurant, maintaining aesthetics can add another dimension to the experience, but all other functives from our FAST diagram are needed for both customer groups to achieve our product's base level of functionality. To effectively serve our customer groups while streamlining manufacturing and assembly processes, adopting a modular product architecture is crucial. This means while the products within the family share base design features called platforms, other features called modules are different, allowing functional differentiation within the family. For our device, the one module we have identified is the grate. Customization of the grate allows for different shapes and sizes of food to be produced, as well as ensuring uniform size for professional chefs. The grate was also the most expensive component in our BOM, so making that a module could introduce cheaper design choices for home cooks. All other components in the original design remain classified as platforms, as they are unaffected by the target audience.
For our redesign, we first split the grate into two modular components, a front grate shown in blue and a top grate shown in purple. The frame of the dicer has tracks parallel to each grate to support the grate's insertion. We further added a channel to prevent the top grate from sliding on the tracks. We then reduced the size of the top and back presser teeth to mesh with all modular grate options. We offer 4 options for the front and back grates, including slicing and dicing with either coarse or fine results. Together, these options allow for 24 possible outcomes of the dicer. Finally, to best understand the changes between the original and altered design, we created product family design diagrams using delayed differentiation. The original sequence shows no possible variance given its singular grate. By contrast, our modified dicer allows for 24 variants as shown in the color-coded circles, which are divided based on which top and front grate are inserted. While for the original dicer, the grate is added second as a singular piece, the front grate is added 7th with the top grate following. The modified design also adds the channel. Thank you for listening to our presentation. We hope you enjoyed our analysis and recreation of a food dicer.